Lecture 10.1, Parametric Functions. Here we have Mark Twain's boyhood home in Hannibal, Missouri. When Samuel Clemens, who later became Mark Twain, wrote Tom Sawyer, he wrote about some of his own experiences. And to the right, we see the location of the famous fence that he used in his story. In the background is a stone wall that was built by the Civilian Conservation Corps in the 1930s to act as a fire break to protect the house from a possible fire at the lumber yard in the next lot. Here we see Mark Twain moved up in the world. This is Mark Twain's home in Hartford, Connecticut. This is actually the location where he wrote his most famous novels. He didn't earn the money for this house by writing the novels. He married well, and the house was a gift from his father-in-law. In Chapter 1, we talked about parametric equations. Parametric equations can be used to describe motion that is not a function. We have two separate equations in terms of t. For example, x equals f of t, y equals g of t. If f and g have derivatives at t, then the parametrized curve also has a derivative at t. The formula for finding the slope of a parametrized curve is dy dx equals dy dt over dx dt. This makes sense if we think about canceling dt. We assume that the denominator is not 0. To find the second derivative of a parametrized curve, we find the derivative of the first derivative. d squared y dx squared is the derivative with respect to x of y prime. That is dy prime dt over dx dt. Steps are 1. Find the first derivative, dy dx. Step 2. Find the derivative of dy dx with respect to t. Step 3. Divide by dx dt. Example. Find the second derivative with respect to x, d squared y dx squared, as a function of t if x equals t minus t squared and y equals t minus t cubed. Step 1. Find the first derivative, dy dx. y prime equals dy dx equals dy dt over dx dt, which is 1 minus 3t squared over 1 minus 2t. Step 2. Find the derivative of dy dx with respect to t. So we have dy prime dt equals d dt, 1 minus 3t squared over 1 minus 2t, which gives us negative 6t times 1 minus 2t minus 1 minus 3t squared times negative 2, all over 1 minus 2t quantity squared. Notice here we used the quotient rule. We clear the parentheses and collect like terms. Step 3 is to divide by dx dt. So d squared y over dx squared equals dy prime dt over dx dt. Or in this case, 6t squared minus 6t plus 2 over 1 minus 2t quantity squared divided by 1 minus 2t. Simplifying, we get 6t squared minus 6t plus 2 over 1 minus 2t quantity cubed. The equation for the length of a parametrized curve is similar to our previous length of curve equation. L equals the integral from a to b of radical dx dt squared plus dy dt squared dt. Notice the use of the Pythagorean theorem. Likewise, the equations for the surface area of a parametrized curve are similar to our previous surface area equations. The surface area for the revolution about the x-axis, where y is greater than or equal to 0, is S equals the integral from a to b 2 pi y times radical dx dt squared plus dy dt squared dt. So in this case, y is the radius, and the second part of the expression is the length of the curve. If we want to revolve around the y-axis, where x is greater than or equal to 0, now the radius would be x. This curve is x of t equals t plus sine 2t, and y of t equals t plus 2 cosine 5t.